Right now, you believe that the Andromeda Galaxy is 2.5 million light-years away from you. You believe the nearest star is 4 light-years away. You believe distance in space is real, measurable, absolute. But what if every single measurement you have ever made of cosmic distance is wrong? What if distance itself is not a fundamental property of reality, but a trick your brain plays on you? What if at the deepest level of physics, space has no distances at all? What I am about to show you will permanently destroy your understanding of what space actually is. Distance feels like the most obvious thing in the universe. You are sitting some distance from the screen you are watching this on. The moon is 250,000 miles away. The sun is 93 million miles away. These distances feel real, absolute, permanent. Distance is just how far apart things are. It seems like the simplest concept in all of physics, but simplicity is often the mask that the deepest mysteries wear. And distance, the most seemingly obvious property of space, turns out to be one of the most profoundly misunderstood concepts in all of science. Distance in space is not what you think it is. It is not fundamental. It is not absolute. It is not even real in the way your intuition tells you it is. And the journey to understanding why will take you through quantum mechanics, general relativity, holography, and the very foundations of what space itself actually is. Let me start with something you might think you already know: the speed of light and what it tells us about distance. When astronomers say the Andromeda Galaxy is 2.5 million light-years away, they are making a statement that sounds like a distance measurement but is actually a time measurement. A light-year is the distance light travels in 1 year, so saying something is 2.5 million light-years away means light takes 2.5 million years to travel from there to here. But here is the problem. You are not measuring where Andromeda is right now. You are measuring where it was 2.5 million years ago when that light was emitted. By the time the light reaches your telescope, Andromeda has moved. It has been moving for 2.5 million years. The distance you measure is the distance to a ghost, to where Andromeda was millions of years in the past, not where it actually is at this moment. And due to the expansion of the universe, the actual current distance to Andromeda is different from the distance the light traveled to reach you. Space expanded during the 2.5 million years the light was traveling, so the distance the light traveled is not the same as the current distance between you and Andromeda. Every cosmological distance measurement conflates at least 3 different distance concepts: the distance light traveled, the distance at the time of emission, and the current distance accounting for expansion. These are all different numbers. Which one is the real distance? The answer is that none of them is more real than the others. They are all valid measures of separation, depending on what question you're asking and what reference frame you're using. There is no single fact of the matter about how far away a distant galaxy is. Right now, distance at cosmological scales is observer-dependent and definition-dependent. It is not an absolute fact about reality. But this is just the beginning. Special relativity goes much further in destroying the absoluteness of distance. Einstein showed in 1905 that distance is relative, not approximately relative or kind of relative, absolutely fundamentally mathematically relative in a way that depends on how fast you are moving. Here is the core result. A ruler moving past you at high speed is shorter than an identical ruler at rest, not because the ruler is physically compressed, not because something is pushing on it, but because the geometry of space-time is such that a moving object occupies less space in the direction of motion than the same object at rest. This is length contraction, and it is a real measured, experimentally confirmed fact. At 10% of light speed, an object is contracted by about 0.5% in the direction of motion, small but measurable. At 90% of light speed, it is contracted to about 44% of its rest length. At 99% of light speed, it is contracted to about 14% of its rest length. As you approach light speed, length approaches 0. What does this mean for cosmic distances? It means that distance is frame-dependent. If you are on a spaceship moving at 99% of light speed toward Andromeda, the distance from you to Andromeda is not 2.5 million light-years. It is 2.5 million light-years divided by the Lorentz factor, which at 99% light speed gives you a distance of about 350,000 light-years. You and someone standing still on Earth would measure completely different distances to the same galaxy. Both measurements are correct in their respective reference frames. There is no absolute distance. At the speed of light, the contracted distance would be 0. From a photon's perspective, if it had a perspective, which we established in a previous video, it does not. The distance from its source to its destination is exactly 0. Every cosmic distance is 0 for a photon. The entire observable universe has 0 size from the reference frame of light itself. So distance in space is already not absolute. It depends on your speed. It depends on your reference frame. Different observers measure different distances between the same 2 points, and all their measurements are equally valid. There is no fact of the matter about the true distance between 2 points in space independent of who is measuring it and how they are moving. But even this is not the deepest level at which distance breaks down. General relativity goes further. In general relativity, space itself is curved. Mass and energy warp the geometry of space-time. Near a massive object, space is curved significantly. This means that the distance between 2 points is not determined by some fixed background geometry. It is determined by the distribution of matter and energy between and around those points. Near a black hole, space is so curved that the distance from outside the event horizon to the singularity inside is effectively infinite. Even though the black hole has a finite radius as measured from the outside, an infalling observer experiences the inside of a black hole as having enormous volume far larger than the black hole appears from the outside. The interior of a black hole contains vast amounts of space that are not accessible from outside. This reveals that distance is not a fixed property of space. It is determined by the geometry, which is determined by matter and energy. Change the distribution of matter and energy, and you change all the distances in the universe. Distance is not a backdrop against which physics happens. It is itself a physical quantity that changes depending on the physical configuration of the universe. Curved space also means that the shortest path between 2 points is not a straight line. In curved spacetime, the shortest paths are called geodesics, and they follow the curvature of space. The distance along a geodesic depends on the curvature, and the curvature depends on the mass and energy distribution. 2 points that are close together in flat space might be far apart along the geodesic if there is a massive object between them, or might appear close together due to gravitational lensing bending light around the massive object. Even the concept of 2 points being at the same location gets weird inside a black hole due to the extreme space-time curvature. 2 points that are at the same spatial location according to one coordinate system can be at vastly different locations according to another coordinate system. The coordinates we use to label points in space-time are arbitrary. Different coordinate choices give completely different descriptions of which points are near each other and which are far apart. This is not just a mathematical technicality. Physical effects depend on coordinate choice. What looks like a strong gravitational field in one coordinate system looks like flat, empty space in another. What looks like a huge distance in one coordinate system looks like a tiny distance in another. The coordinate invariant facts about space-time are about its geometry and topology, not about simple distances between points. Now we come to the deepest and most radical way in which distance in space is an illusion. Quantum entanglement and the holographic principle. Quantum entanglement is perhaps the strangest phenomenon in all of physics. When 2 particles interact and become entangled, they form a single quantum system described by one wave function, no matter how far apart they are subsequently moved. Measure a property of one particle, and you instantly know the corresponding property of the other particle, regardless of the distance between them. Einstein called this spooky action at a distance and spent years trying to prove it was impossible. He was wrong. We have confirmed entanglement in thousands of experiments. 2 entangled particles can be on opposite sides of the observable universe, and they remain one quantum system. Spatial separation does not break entanglement. Distance does not weaken it. 2 entangled particles that are billions of light years apart are quantum mechanically closer to each other than 2 unentangled particles that are touching. This reveals something profound. Quantum mechanical proximity and spatial proximity are completely different things. 2 particles can be spatially distant but quantum mechanically connected. 2 particles can be spatially adjacent but quantum mechanically independent. Spatial distance does not capture what is actually happening at the level of quantum reality. Physicist Juan Maldacena made one of the most revolutionary discoveries in the history of theoretical physics in 1997. He discovered a precise mathematical equivalence called the ADS-CFT correspondence between a theory of gravity in a certain curved spacetime and a quantum field theory with no gravity living on the boundary of that spacetime. The gravity theory lives in a space with one more dimension than the boundary quantum theory. Yet the 2 descriptions are completely equivalent. Every observable in one theory has a precise translation into an observable in the other theory. They describe exactly the same physical reality from 2 completely different perspectives. This is the holographic principle in its most precise mathematical form. The physical reality we experience in 3 dimensions of space can be completely and exactly described by a theory living on the 2-dimensional boundary of that space. The 3rd dimension of depth, the dimension that gives us our sense of depth and distance, is not fundamental. It is emergent. It arises from the quantum entanglement structure of the boundary theory. Think about what this means for distance. In the 3-dimensional bulk theory, You have distances. Things are close or far apart. Gravitational effects depend on distance. The geometry of space-time determines distances. All of this seems fundamental and real, but in the two-dimensional boundary theory, there is no bulk distance. The two-dimensional boundary theory has its own distances. It's two-dimensional geometry. But the three-dimensional depth, the distance into the bulk, is not a geometric distance in the boundary theory. It corresponds to something completely different. Specifically, it corresponds to the energy scale of the boundary theory. High-energy processes in the boundary theory correspond to small distances from the boundary and the bulk. Low-energy processes correspond to large distances from the boundary. What we perceive as distance in the third dimension of space is actually energy scale. In the underlying quantum theory, distance is not fundamental. It is a way of describing quantum mechanical relationships between degrees of freedom at different energy scales. Depth in space is an emergent property that arises from the structure of quantum entanglement in the boundary theory. This is not an approximation or an analogy. This is an exact mathematical equivalence proven to extraordinary precision. Space, specifically the radial distance dimension in the holographic picture, is literally emergent from quantum entanglement. Recent work by physicists Mark van Ramsden, Brian Swingle, and others has made this connection even more explicit. They have shown that the geometry of space-time, including all its distances and curvatures, is determined by the entanglement structure of the underlying quantum fields. Specifically, a concept called entanglement entropy, which measures how quantum mechanically entangled different regions of a quantum system are, determines the geometry of the corresponding space-time. Regions of space-time that are close together correspond to strongly entangled regions in the quantum description. Regions of space-time that are far apart correspond to weakly entangled regions. Distance in space is entanglement in quantum mechanics. These are two descriptions of the same underlying reality. Van Ramsden demonstrated this with a beautiful thought experiment. Take the quantum state of the boundary theory and reduce the entanglement between two halves of it. What happens to the bulk space-time? The bulk space-time splits into two disconnected pieces as the entanglement is reduced. Continue reducing entanglement to zero, and the two halves of the bulk space-time become completely disconnected with infinite distance between them. Restore the entanglement and the two halves reconnect and the distance decreases. Space-time connectivity, the fact that different regions of space are connected to each other with finite distances, is literally created by quantum entanglement. Remove entanglement and space falls apart. Add entanglement and space is stitched together. Distance is not a property that space has independently. Distance is a manifestation of quantum entanglement between the degrees of freedom that constitute space. This insight has led to one of the most exciting recent developments in theoretical physics. The ER equals EPR conjecture proposed by Moldsina and Leonard Susskind himself. Einstein-Rosen bridges, which are wormholes connecting two distant regions of spacetime, are denoted after Einstein and Rosen, who first described them mathematically. Einstein-Podolsky-Rosen pairs, which are maximally entangled quantum particles, are denoted EPR after the famous 1935 paper by Einstein, Podolsky, and Rosen. The conjecture states that ER equals EPR. That is, an Einstein-Rosen bridge between two black holes is the same as an EPR entanglement between the two black holes. A wormhole connecting two distant regions of space is equivalent to maximum quantum entanglement between those regions. The geometric connection through a wormhole and the quantum mechanical connection through entanglement are the same thing described in two different languages. What does this mean? It means that entangled particles are connected by a kind of quantum wormhole, a geometric bridge through space-time created by their entanglement. Two particles that appear to be spatially distant from each other because you cannot see the quantum bridge between them are actually geometrically connected through that bridge. The distance between them is an illusion created by looking at the wrong level of description. Our ordinary notion of distance, the distance you measure with a ruler or a laser rangefinder, is the large-scale emergent description underneath it. At the quantum level, the real structure is entanglement. Two entangled particles are not distant from each other in any fundamental sense. They are connected. Distance is a macroscopic illusion that arises when you average over quantum details. Loop quantum gravity offers yet another perspective on why distance is not fundamental. In loop quantum gravity, space-time is not smooth and continuous at small scales. Instead, it is composed of discrete quantum units, tiny chunks of space called spin networks. The nodes of a spin network represent quanta of volume. The links between nodes represent quanta of area. Distances in loop quantum gravity are not continuous quantities. They are discrete quantized, coming in minimum units related to the Planck length, which is about 10 to the 35 meter. At scales below the Planck length, the concept of distance becomes meaningless, not just unmeasurable meaningless. There is no physical fact about whether two things are separated by less than a Planck length, because spatial separation below this scale is not a meaningful concept. Space is not infinitely divisible. It has a smallest unit, and below that unit, the very idea of distance breaks down. This means that our smooth, continuous space with its infinite precision distances is an approximation. It works extremely well at scales much larger than the Planck length, but it is not the fundamental reality. Fundamental reality is a discrete quantum network where classical distance emerges as a large-scale statistical property of the network. The way temperature emerges from the average motion of molecules, even though individual molecules do not have a temperature. Distance in space is therefore doubly illusory. At the quantum gravity scale, space is discrete and distance loses its classical meaning entirely. At larger scales, distance emerges as an approximate description of the underlying quantum network structure. But this emergence means distance is not fundamental, it is derived. The implications of all this are staggering. Two galaxies that appear separated by millions of light years might be connected by quantum entanglement in ways that make that spatial distance physically irrelevant for quantum processes. The apparently vast distances between stars might be at the quantum level descriptions of entanglement structures rather than fundamental gaps in space. The universe that appears to stretch across billions of light years might be at the deepest level a quantum system where what matters is not spatial geometry but quantum connectivity. This does not mean you can instantly teleport across the galaxy by exploiting quantum entanglement. Entanglement does not allow faster than light communication or transport of matter. The quantum connection between entangled particles does not create a traversable tunnel for information or energy. The distance is illusory at the fundamental level, but the constraints on what can physically happen between distant regions remain in place. You cannot exploit the underlying quantum connectivity to violate causality. But it does mean that our entire picture of the cosmos as a vast empty space with things scattered across it at enormous distances is fundamentally misleading. The universe is not primarily a spatial structure, it is primarily a quantum structure. The spatial distances we observe are a macroscopic emergent description of the quantum entanglement architecture of reality. Think about what this means for how you see the night sky. When you look up and see the Milky Way stretching across the darkness with stars at distances of hundreds and thousands of light years, you are not seeing fundamental spatial separations. You are seeing the large-scale average of a quantum entanglement network. The apparent distances are real as macroscopic descriptions, but they are not the bottom level of reality. When you look at the Andromeda galaxy and think about the 2.5 million light-year gap between us and it, remember that this distance is frame-dependent, observer-dependent, definition-dependent, and ultimately emergent from quantum entanglement structures that do not themselves speak the language of spatial distance. When cosmologists measure the scale of the observable universe at 93 billion light-years and describe it as unimaginably vast, remember that this vastness is a description in the approximate language of classical geometry. In the underlying quantum description, there are no 93 billion light-years. There are quantum states, and their entanglement patterns and the geometry, including all those distances, emerges from those patterns. Distance in space is real, the way that temperature is real. You can measure it, you can feel it, you can build technology based on it. But it is not fundamental the way quantum states are fundamental. It is an emergent, approximate, observer-dependent description of something deeper that has no distances. The universe is not a collection of things scattered across a vast space. The universe is a quantum system, and what we call space with all its distances and geometries is the way that quantum system looks from the inside when you are a macroscopic being made of trillions of atoms interacting at energies far above the quantum gravity scale. You are not separated from the stars by light years. You are connected to them through a web of quantum entanglement whose large-scale description we call space. Every particle in your body is quantum mechanically connected to particles throughout the cosmos. The apparent distances between you and everything else are the macroscopic shadow of quantum connections that have no spatial description at the fundamental level. This is what distance in space really is, not a fundamental property of reality, not an absolute fact about how far things are from each other, but an emergent approximate observer-dependent description of quantum entanglement architecture. A useful fiction that we mistake for fundamental reality because we are too large to see the quantum structure underneath. The universe is not vast. The universe is quantum. And in the quantum description, there are no distances.